This video demonstrates the use of QDSL models for embedded renewable generation and variable loads. QDSL is used to provide user-defined models of the steady-state behavior of various power system equipment elements, so that the results of a load flow calculation reflect this behavior. The QDSL models used in this LV distribution network can be found in the Global DigSilent library. Study Case 3.1, QDS, EV and battery, should be activated. The 0.4 kV network in this project contains not just LV loads, but also models of PV generation, electric vehicles and battery storage devices. We will first look at how these elements work, then run the quasi-dynamic simulation to see their effect in the local network. The elements of interest are modeled in FEEDRFD094, shown here. First, let us look at one of the PV generators. Its active power output is determined using the internal solar calculation model. This calculates the output of the generator based on its location, i.e. the latitude and longitude of its connection point, together with the date and time. The details of the calculation can be found in the technical reference for the element. There are 5 loads representing electric vehicles, whose active power demand is determined by QDSL models. Let us look at one of these vehicles. On the load flow page, we see that this load is controlled by a QDSL model. The QDSL code at the core of this model is found in the QDSL type object. On the description page, the model and its parameters are described. The QDSL model of the electric vehicle represents a randomized daily charging process, which means that it mimics the randomness of human behavior. The owner of the vehicle might arrive home and start charging the vehicle at any time between 1800 and 1900 hours. The state of charge of the vehicle will also vary depending on how far it has been driven that day. Therefore, for each day of the simulation, the model randomly generates a starting time for charging, and randomly sets the initial state of charge of the vehicle, within the constraints of the input parameters. There are 4 batteries in the network. Each is represented by a static generator of plant category storage, and is placed in the network with a load, and a PV generator. Such batteries can be used to maximize the local consumption of energy from the associated PV generator. When the energy supplied by the PV generator is more than is required to support the local load, some of the output can be stored in the battery. The battery can then provide energy when there is little or no PV generation. The batteries are controlled by QDSL models, which determine for each time step whether the battery should be storing or releasing energy. The operating mode of the battery is dependent on the power flow measured on the connecting line. These parameters define the maximum power at which the battery can operate. By comparing the measured power with these input parameters, the QDSL model determines the required level of power input or output for the battery. Let us now run a quasi-dynamic simulation, using this icon to open the command dialog. The command is already configured, but we will decrease the step size to 15 minutes, so as to see a more detailed analysis. The command is executed. Let us look at the results on the plots that have already been prepared. Here on the EV charging plot, we can see the charging activity of the 5 vehicles. The random start times and initial states of charge are reflected in the differing charging patterns each day. This energy plot shows the PV output and battery storage activity. Note that this plot uses a curve stacking setting, giving a resultant profile. If we remove this flag, we can see the PV and storage profiles separately. This plot shows the active power of the batteries. As a rule, the batteries store the most energy during the day, when the PV systems are generating. But we can see quite some variation between the different storage systems. This is partly because of different model parameters, but also because the loads that they support vary in their load profiles. And these plots show the detail for each battery and its associated load and PV plant. Finally, if we return to the feeder representation, we can see a summary of the results of the quasi-dynamic simulation for this feeder.